Now that we've got the basics of Big O notation down, we can finally hop into our first sorting algorithm, selection sort. By definition, a selection sort is a simple, in-place, comparison-based, unstable sorting algorithm which slowly builds an unsorted list into a sorted list by repeatedly searching for the smallest value and placing it in its correct location. Let's break down the adjectives I just used to describe the algorithm one at a time, because they may be new to you. An in-place algorithm is one in which we sort the list without any extraneous memory. Basically, the algorithm sorts the list without having to allocate any extra memory in the computer. When I state that the algorithm is comparison-based, that just means that we sort the list by comparing the elements in that list to one another, as opposed to some other method. Finally, an unstable algorithm is one in which the order amongst duplicate elements is not preserved. This is a tough concept to wrap your head around completely, so let's use an example. Say you were sorting a shuffled deck of cards. In a standard shuffled deck, there are 4 versions of the card with a 10 on it. The 10 of spades, clubs, diamonds, and hearts. For the sake of this example, let's assume we're hiding the other 48 cards in the deck and just focusing on the 10s. We can sort the deck using the numbers on the card, but there are distinct differences in the different kinds of 10s. For example, a 10 of spades is different from a 10 of hearts. Well, in a stable sorting algorithm, the order that these 10s appear in our shuffled deck would be preserved when we sort the deck. So the same order in which they appear on your screen now is the same order they would be in once the deck is sorted. In an unstable sorting algorithm, these cards might be in a different order once the list is sorted, because unstable sorting algorithms fail to preserve the order of duplicates. So as you can see, the 10 of hearts and 10 of diamonds switched places with one another once we shuffled the deck. Since they all technically have the same value, the list is still sorted. The only difference is that the order of the cards as they appear in the deck was not preserved. Translating this to numbers, if we have a list which has 4 integers 5s, a stable sorting algorithm will preserve the order of those 5s, while an unstable sorting algorithm will not. So, a stable sorting algorithm will make sure that in the final sorted version of the list, the first 5 in the unsorted list is the first 5 in the sorted list. The second 5 in the unsorted list is the second 5 in the sorted list, and so on. In contrast, an unstable algorithm does not guarantee this. The relative locations of the 5s might get mixed up or even completely replaced. Okay, going back to selection sort. A good way to look at selection sort is that we essentially split the unsorted list up into 2 parts, with the sorted half on the left and the unsorted half on the right. At the beginning, the left half is empty, and the right half contains the entire unsorted list. Then, slowly but surely, we continue to pull the minimum value from the unsorted half of the list and place it in the sorted half. We then repeat this process until we are left with a completely sorted list. That's just a general way of looking at things though. The actual algorithm works something like this. We start off with 3 variables to keep track of. A counter index to keep track of how much of the list we've already sorted, a traversing index to keep track of where in the list we are traversing to, and an integer to hold onto the index location of the current minimum value in our list. We then start by setting the counter to be equal to 0, the minimum index to be equal to the counter, and the traversing index to be equal to 1 plus whatever the counter is. The next step is to search through the unsorted part of our list, starting from the counter and going through to the end of the data, increasing our traversing index as we go. For every element that we pass over, we compare the value at the traversing index to the one that is currently stored in the minimum index. If the value at the traversing index is less than the value currently stored at the minimum index, we then set the minimum index to whatever our current traversing index is. This essentially means that we replace the index which we thought contained the minimum value in our list with the index we are currently on, since we now know that the value stored at that traversing index is less than the one stored at the old minimum index. We continue this process, increasing the traversing index each time, and test the entirety of the unsorted list. After traversing from the counter index to the end of the list, we now have the index location of the minimum value contained within our unsorted list stored in the minimum index. The next step is to swap the values contained at our counter and the minimum index. This puts the minimum value in the unsorted part of the list in its correct place in the sorted part of the list, and puts the integer that was stored at our counter further on in the unsorted part of the list, to be placed in further down the road. Finally, we increase the counter by 1, set the minimum index to be equal to the counter, and set the traversing index to be equal to 1 plus the counter, so that we're ready to go through the unsorted part of the list yet again. Now we just repeat steps 3 through 6 until the list is sorted. Now with many of these algorithms, it's really hard to visualize how they actually work without an example. So let's take this step-by-step process that we've just created and put it into practice, both with a small example by hand and then through a large visualization so you can really see how the algorithm works. To keep things simple for the hands-on approach, let's take a list of 5 numbers in a random order and sort them using selection sort. Following our steps from the last segment, we'd start off by defining our 3 variables: counter, traversing index, and minimum index. Counter and minimum index both get set to 0, and the traversing index gets set to 1 plus the counter, so in this case the integer 1. Let's represent these variables on our list visually. The light blue border signifies the current index location of the counter, and the dark blue border represents the current index location of the traversing index. If an index is highlighted in purple, that simply means that that is the location of the current minimum index. We start at the traversing index and compare the value at that location to the one stored at the minimum index. Immediately, we see that the stored value at our traversing index, the integer 3, is less than the value stored at the minimum index, the integer 4. Therefore, we set the minimum index to be 1 instead of 0, since we now know that that contains the minimum index so far. Moving on, we increase our traversing index by 1 and continue along our list. Next up, we would compare the value stored at the third index, the integer 5, to the value stored at the new minimum index, which now contains the value 3. Since 5 is greater than 3, no swaps are necessary, and we can increase our traversing index once again. Up next, we compare 3 to 10, and since 3 is still the lowest number amongst the two, no adjustments need to be made. Traversing index gets increased, and we finally compare 3 to the last element in the unsorted part of the list, the integer 1. Since 1 is less than 3, we set minimum index equal to the index location 4. We've now completed one full pass of the list and have the minimum value index location stored. Next, we swap the values contained within the counter index and the minimum index. This entails exchanging 1 and 4. We then increase the counter by 1, set the minimum index to whatever the counter is, and set the traversing index to again be 1 plus the counter, in this case 3. Now we just do the whole process over again. Luckily, as we get further and further into the list, the number of elements we have to compare decreases. Once again, we repeat our steps. We compare 3 to 5, and since 3 is less than 5, keep the minimum index set to 1. Then we increase the traversing index and compare 3 to 10. We again don't swap for the same reason as before. Finally, we increase the traversing index one more time and compare 3 to 4. Since 3 is less than the value, we keep all of our data the same. No swapping is necessary since we lucked out by having the minimum value of the unsorted part of the list stored in the first index. Again, we increase the counter, set the traversing index to that plus 1, and set the minimum index to the counter. 5 gets compared to 10, and since 5 is less than 10, we keep things the same. Then we compare it to the last element in the list, and since 4 is less than 5, we set the minimum index to be equal to index location 4. We've again reached the end of our list, and so we swap the value contained at the counter index, the integer 5, with the value contained at the minimum index. We're now left with only 2 unsorted elements. We increase the counter, the traversing index stays at 4, and we set the minimum index to the value of the counter, or the integer 3. In this final pass, all we do is compare 10 to 5. Since 5 is less than 10, we set the minimum index to be equal to index location 4, and since we've reached the end of our list, swap the 2 remaining values to give us a sorted list. And there we go. After a lot of swapping and hard work, we've successfully sorted our list of 5 elements using selection sort. Luckily for us, we won't have to do all of this by hand. We can simply implement the pseudocode for the algorithm that we talked about previously into our programming language of choice, and then the computer will do all of the hand comparing and swapping for us. Speaking of implementing sorting algorithms, I'm debating having another video for each algorithm in which I go over how to implement each algorithm in 3 different languages: Java, Python, and C++. There should be a poll in the top right corner to gauge interest in whether or not you guys would be interested in something like that, or you can let me know in the comments below. If enough people are excited about something like that, I'll make it happen. Back to selection sort. To show you the algorithm on a wide scale, let's pull up a sorting algorithm visualizer that I've been working on for a while, and watch selection sort go to work on a list of 25 elements with 0 milliseconds delay. Did you miss it? Let me run it again. Did you catch it that time? Probably not. You see, the computer can handle so many operations per second that if we don't add a delay onto our visualization program, it'll look like nothing ever happened. The computer can run through a list of 25 elements pretty much instantaneously. So if we want to see the algorithm in action, we need to put a delay on it. Once we do that, you can see things become much more clear. As you can see, the sorted list is slowly being built up from the left side of the dataset. Each pass-through results in another sorted element. And just like that, the sort is finished. Let's run it one more time, only this time on a much larger dataset with a smaller delay. What I want you to notice with this pass-through is that as we build the sorted part of the list larger and larger, you'll notice that the unsorted part of the list becomes a lot more similar in terms of the elements stored in it than it was before. This is mainly due to the fact that if we keep taking out the minimum value and swapping it, eventually the elements in the unsorted part of the list will trend towards the maximum value. That's enough for visualizations. I find these visualizations fascinating, and it seems like a lot of people on YouTube do as well. Because of this, accompanying every lecture-style video on a certain sorting algorithm will be a second video the day after containing a few visualizations of that algorithm with different datasets and delays. So stay tuned for that. Now that we know what selection sort is, as well as how it works, along with an example and a visualization, let's jump into its time and space complexity. Because selection sort requires the use of 2 nested for loops, one to increase the counter after each pass, and one to cycle through the traversing index to find the minimum value, no matter what case scenario you use, its time complexity will always be O of n squared. This results from the fact that even if you are randomly given a list which is already in sorted order, the computer will still follow the selection sort process. It will still cycle through each index in the list and check for the minimum value, even though the minimum value will always be the same as the counter index. The way that the algorithm is coded leaves no room for cutting corners or saving efficiency, and that's why all 3 of its time complexity equations, best case, average case, and worst case, are O of n squared. As for space complexity, since the algorithm is in place, like we mentioned at the beginning of this segment, its space complexity is O of 1. If you remember back to our episode on time and space complexity, this simply means that no matter the size of the list, the algorithm will create no additional memory to help sort it, which is very useful for programmers trying to save space. Selection sort's time and space complexities are pretty simple, and that's because selection sort is, well, a simple algorithm. I mean, it makes sense that we're not starting with the big baddies of the sorting algorithm community. Selection sort is a simple enough sorting algorithm to get you guys used to sorting algorithms in general, and also what the structure of this series will be. This episode really sets the tone for those to come. Because of this, though, selection sort doesn't get that much use in practical computer science applications. You're not going to be finding this algorithm as the back end for companies like Google or Apple. That's not to say it's useless, though. Because of its simplicity, selection sort is a solid algorithm to use on small lists in which you have memory constraints. Because remember, it doesn't create any auxiliary memory in the computer. It also pops up in a lot of technical cases, such as job interviews or exams, because of its foundational relationship to computer science and sorting algorithms. So while it may not get much practical use, the lessons that selection sort teach us carry over greatly to each of the other algorithms, so it's a perfect fit for the first one in this series. And with that wraps up our discussion on the selection sort, a basic sorting algorithm which sorts the list by repeatedly going through the data and placing the minimum value at the lowest unsorted index. While this algorithm isn't as complicated or efficient as others that we'll talk about, it's foundational for the rest of the series. If you're confused about anything, please check the description for timestamps to take you to each of the individual sections. If not, that's all I have until next week when we hop into our second sorting algorithm, odd-even sort. Make sure to check out the other videos in this series, or take a look at Sean's new series, Remastering Our Introduction to Programming series.